We have talked about Poincare inequality multiple times before, and today I want to show one of its consequences, which gets used very often in different contexts, including in general metric measure spaces. But for today, I'm going to focus on Rn equipped with a measure, a Borel measure that might be different from the Lebesgue measure. And I'm assuming that this measure gives positive and finite quantity to every cube. So instead of balls, I'm working with cubes, which is geometrically a bit nicer. And notation-wise, as is common, so u subindexed with a set means the average value of a function u on that set. And the average value of a function on a set will be denoted simply by putting this line through the integral, just to keep notation simpler. And we say mu, the measure, satisfies a p Poincare inequality, where p is some number bigger than 1, if there exists some constant c, where for every cube and every Lipschitz function on the cube, we have the inequality. So what is the corollary that I'm talking about? So the corollary is basically saying that, let's not get too technical, it's saying that if two cubes, say q1 and q2, are close to each other and their sizes are comparable up to a constant, then average value over q1 minus average value over q2 is small. So that means the average values of the function will be comparable on these two cubes if the cubes are comparable, near each other and of similar size. And the proof of this is the reason really I'm showing you this, because every time I do this, it's just such a joy to do this calculation. So the specifics, the corollary will follow from this lemma, which is more explicit and easier to understand. So you will have this time a cube 0, and your other cube will be actually included inside it. So we have q1, so these are part of the assumptions. Suppose it's a special case of corollary, but will be strong enough to imply it. So q1 is subset of q0, so that definitely makes them close to each other, but also it's not too small, so I'm not looking at a tiny cube here. So that means q0 is itself contained in some multiple of q1. So what is a multiple of a q? That means a q with the same center and side length kappa times that much. So here you have to make this kappa large enough to cover this. So this will be probably, so this would be kappa q1. So it's some constant. Suppose we have this geometry, then average value of q1 minus average value over the larger cube will be comparable by some constant, which may be different from the c above, diameter of q0, and then integral over q0 of gradient u d mu pth power and 1 over p. So which is basically the right hand side in the p Poincare inequality. So let's prove this lemma. Okay, let's just compute u of q1 minus u of q0 is equal to, so average value over Q1 of uz d mu z minus this constant. But I can then incorporate the constant into the average integral. So if I take average of a constant, it's just the same. So this comes inside, becomes u at z minus u at q0. So my u is just any generic Lipschitz function, or even Sobolev, because Poincare also holds for them, d mu of z. Now I'm using the fact that if I first take absolute value, so let me put this measure q1 here. Now this is an integral over q1, and if I put absolute value inside, I get a larger integral, d mu of z. And then we realize that if I integrate over a larger set, then I get more. So uz minus u q0 d mu z. And then this is 1 measure of q1. Now what I do here is I multiply and divide by measure of q0, and then this becomes integral average. And now we have Poincare inequality, mu q0, mu q1, and this becomes some c, which is the c from Poincare inequality, diameter of q0, and then integral average of q0, gradient u to the power p d mu, the whole thing to the power 1 over p. Now here we see that we only need to get rid of this expression here, and that is where we have to add one more condition to our measure, condition of doubling, that the measure of twice cube is controlled by c, say c doubling, measure of q. And if we now have this condition, so this is c Poincare, and then there will be a constant depending on kappa, because if you double q1 enough times, so q1, then 2 times q1, and then 4 times q1, and ultimately this will be larger than kappa q1, which already is larger than q0. So after a predictable number of times, depending on kappa, this will be cp, and this will be cd to some power alpha, which depends on kappa, and then diameter q0, and the integral q0, gradient to the power p d mu 1 over p, which ends the proof of the lemma. So if you have q1 here, and then let's say you have q2 here, so you want to prove that their averages are comparable, but remember our assumption is that they are near each other and their diameters are near each other. So that would show that there is some q0. I'm not even being optimal here, because optimal would actually share some edges. So there's some q0, corollary proof. There exists some q0 such that, well, each one of these is inside q0, and diameter of q1, which we have assumed is comparable to diameter of q2, is in turn comparable up to some kappa to diameter of q0. So if this is kappa, then we have kappa down there. And now we simply use triangle inequality. Average q1 minus average q2 is no more then average Q1 minus average Q0 plus average Q0 minus average Q2, and each one of them we saw was less than 2 times some constant kappa, diameter Q0, which is comparable to diameter of either of them, and this integral average over this big Q0 gradient to the p d mu 1 over p. So yeah, that's a very simple yet very useful calculation. Different versions of it, of course, appears here and there. In the general setting of metric spaces, you won't work with cubes but with balls, but it's all the same. Hope you enjoyed this very nice little consequence of Poincare's inequality. If you have any questions, please put them in the comments, and see you in another lecture soon.